from Sikan Lee, if I remember correctly. Yes, it's about machine learning on TACC. So everybody's going to listen and stop whatever they're doing.
Hey, hello everyone. So I'm here to talk about machine learning on Texas Advanced Computing Center. I am Sikan Li. I'm from the Scalable Computational Intelligence Group. I am a research engineer and I work on machine learning techniques for large data set. Yeah, let me first introduce you to TACC. So what is this Texas Advanced Computing Center? So we are a research center at UT Austin. Currently, we have about like 180 staff and more than a third of us have like PhD degree. We are funded by significant investment from UT System, NSF, NIH, DOD. Also, it's about 15,000 square feet of data center and total capacity of 12 megawatt. We design, build, manage, and operate about a dozen big machines at a time. And we're developed and host dozens of scientist gateways. So our mission is to enable discoveries that advance science and society through the application of advanced computing technologies. Okay, so who are the tech users? So there are approximately 4,000 active projects representing 150 fields of science on tech. We got 15,000 annual command line users and about 80,000 annual users via the portals like the tech analysis portal. We do partnerships with UT System and SF Access Industry, and we also hold like educational programs. Currently, there are about 7 billion compute hours run annually. 5 billion files are processed annually, and we currently store about 100 petabyte of data. Okay, sounds like a lot of users. Why do they use tech? What's the advantage of this, our center? So tech is an easy way to scale up existing computational research. You can gain access to the latest hardware instead of like purchasing them for your lab. You can get access with gateways and portals for common domain-specific workflows. It's very easy to store, manage, and share large data sets if you use tech. And you can add computational data analysis to experimental research. It's an easy way to add a computational component to modern course or workshops. And you can collaborate with domain experts that works for tech. If you are intrigued, here are the ABC steps to start working on tech. First, you need to create an account. And then since I guess most of you are already iHARP users, you can skip the step where you create the project because there's already an active iHARP allocation on tech. What you need to do is just skip to step 3 where you can send a ticket or ask your PI to add you to this allocation, and then you're ready to log in to a cluster, upload your data, and you have your computational resources ready. Just to reminding that we have a lot of training materials available. It's online, a lot of them are free. You can learn about tech and how to get things down there. And also there's this portal where you can send tickets to ask any questions related to your project, related to your account. And for iHARP users, I would suggest you to always indicate iHARP at the beginning of your title so we can give you like faster response. And also there's this tech computing page for iHARP here. There are more kind of resources, menus, links there where you can look for ways to use this computational resource. And also if you're interested in machine learning, and you can like just walk on into this machine learning office hours with me. So if you get into this Zoom link on Monday, 1 to 2 p.m. Central Time, I will be there. You can ask me anything about machine learning. Okay, finally, that's the introduction about TACC, and we're gonna talk about machine learning. To start with, I cannot emphasize enough on the importance of good data, because the performance of a machine learning model is upper bounded by the quality of the data. So the first thing we want to do before any modeling, before we do any computation, we want to do a quick summarization of our data set, like plot it out, see if it fits your expectation. Does the data make sense? And then we can do some bivariant analysis like this scatter plot or do a correlation plot. The thing we want to look for here is collinearity, because in linear models, collinearity would cause numerical instability. And also when two features are linearly related, the statistical significance would be reduced when we are doing analysis. And then we are going to do some data cleaning before we throw the data into the model. So we will probably deal with missing values. We can either just throw out the data points with missing values, or we can figure out a way to fill in the missing values. And also we will deal with outliers, and like how do we want to decide whether a data point is an outlier. Finally, we can pick a model. So usually we pick the model to start with, depending on the type of the problem we have. Like for classification problem, we usually start with logistic regression, SVM, decision tree models. And for regression problem, we usually start with linear regression or MLP. And for data with time data, we can use RNN or transformer, because those models have like the time information encoded in them. And then once we have a baseline model running, we can consider, oh, it's time to kind of throw more data to my model. It's time to run a bigger model just to get better performance. And that's when you would think about getting your code to run a high performance computing platform like TACC, where you can get access to larger storage and faster computations. So for iHARP users here, you already have allocation to our Frontera supercomputer. On Frontera, the primary computing system, there's more than 8,000 nodes of Intel Cascade Lake. The peak performance is about 39 petaflops. We have this nice storage with more than 50 petabyte disk, good I/O speed, and also there's this GPU subsystem with 90 nodes. Each node is equipped with 4 NVIDIA RTX 5000 GPU. There's also 150 gigabyte of local SSD for faster I/O speed. So this GPU subsystem would be nice if your code is kind of optimized for parallel processing on GPUs. And so you can get access to Frontera through either command line or this Jupyter Notebook application from Tech Analysis Portal, which I find is pretty popular among iHARP users. And once you get your code running on TACC, you probably want to tune your model for better performance. You want to think about how many layers do I really need. You probably want to tune the count of units in each layer and how you want to initialize your variables. And also there are hyperparameters you want to tune for the training, like the learning rate, the momentum, what penalty you want to add into your logistic regression, and what loss you want to do in your gradient descent. And finally, when you start training, you probably want to monitor how your training loss and validation loss change across the training process, and you probably want to stop at a point where the validation loss is the smallest, because we don't want to underfit or overfit our model. So this is just an example of a collaboration of TACC with the project 5 here. We just heard about the project in the morning. It's a physics-informed learning to create a 3D model of the ice bath. So this project, we are trying to predict the bed height of the Greenland ice sheet. We have about 10 gigabyte of data set. It's 187 million entries of data points, and each data point has about 11 features. Our model is a ResNet model with approximately 6 million trainable parameters. And so I worked with the project to make the training process for this model data parallel, so we can utilize multiple GPUs when we're training the model. And this is kind of the result of the training progress, and we can see the test loss would decrease at the first 3 epochs, and then the data would kind of overfit our model, and the test loss would increase. So that's what I prepared for this presentation. Any questions?
Thanks for the presentation. One common challenge people face when using big machines, they don't know which particular types of machine they should use, and how should they parallelize it. And for example, if we really have a large data set, very complicated models, trying just to find the right resources for that particular execution is not easy. What's your recommendations how they should gradually find the best environment for their particular execution?
Well, usually, like, before users kind of move on to TACC, there's already something that works. So if the code like originally runs on your CPU, what I would suggest you start with the CPU resource on Frontera, so that you don't need to change the code much. And then there are kind of different libraries that are optimized for different like hardware. There are versions of code models that's parallelized kind of for GPU, and that's why you want to try them on GPU. Does that make sense?
Yes, you're talking about CPU and GPUs. Like,
Right.
what about like different types of CPUs, different types of GPUs, because they have a much newer generation GPUs coming up every month, but we don't know which one is the best for this particular model.
Yeah, that's why like Frontera is a good starting point, because the GPU on Frontera is kind of smaller, but you don't need to wait for like several days to get your code start running. So usually we would start with a smaller GPU that's easily accessible, and just test the code and see if it runs well, and then you would analyze the code and see kind of what kind of throughput you need, how much memory does it take, and if like the memory doesn't fit the requirements, you probably want to move on to a resource with like bigger memory. And you'll see like if your computation, like if computation is kind of bottlenecking your application, you will see maybe it's time to either like parallelize your code or either to move to a faster machine.
Do you also have an FPGA cluster?
I don't think so.
So this is mainly GPU and CPU based.
We have like CPU and GPU.
Okay.
Right.
Yeah. And I see this is a wonderful computing resource. I wonder what's the cost model for using the TACC service? What's the cost for what's the charge, the price to use?
Oh, we are a research facility, so we don't charge for the node hours. You just write your application, write your like through the portal. Like I think you can apply for node hours once, and then there's kind of this vetting process where we see if it makes sense and the research is proper, you would be kind of given some of node hours. And we only charge for the services we offer, like we do data management, we do code development. Those are the things that you actually pay for, but we don't charge for node hours, if that makes sense.
So this is the supercomputing table, if you're wondering. Yeah. Yeah, so the program used to be called Exceed. Now it's called Access, which is very confusing because it sounds like just a regular word. But it's easy to get a small amount of cycles. To get a larger amount, you have to write more and there's a lag. But usually if you contact someone, they'll help you find your way to what you need. And all of the supercomputing centers save 10% as discretionary that you can just pay for if you wanted to. But usually if you can wait a little bit, you can get whatever you need.
Yeah.
In NSF Spain, I guess I should have said.
Burning question? Okay, what's really great about TACC is the user support. I think Sikan is always on Slack. She has office hours. She's amazing. So I want to say thank you, Sikan, because you never get paid. Thank you to the other two speakers for this session. I think we're going to take a 5-minute break to set up the panel discussion, and we'll be right back.
Thank you,